So we're going to talk about this concept of rotating functions about an axis. This is going to be very cool in a sec. I think this is one of the coolest things ever, because you don't need a crazy math class to do it. I mean, this is calculus 1. It's not easy, but it does give you some crazy things. So we're going to talk about some weird stuff. So let's say I had a function, right? And I practiced, so I had this function right here. And this is f of x, here this curve, and this is the x-axis. And imagine kind of rotating this function around the x-axis. So take this curve for a sec and just start rotating it around. So just rotate the function over so that you can find something interesting happening. So if you rotate the function, and I will draw this out if I can. So if I rotate it, it'll turn out to look like this. And if I rotated it enough, I'll end up with this shape that has been rotated around. So you're taking the function and rotating it about the x-axis, and this is what it kind of traces out. It traces out this three-dimensional little vase thing. And we're going to attempt to find the volume of this. So it's a pretty neat idea that we're taking just a regular old function and rotating it about the x-axis. So my idea here is, how would we find the volume of this shaded region, or the 3D solid? Okay, how would we do that? Well, tell me, let's go back to the original function. I think it looked something like that. We take this area that we cut it off at. So from A to B, right? So from this point on, from A to this end right here. B, that's where it ends. I want to make the 3D effect, you know. So that's the area that we're revolving to make a volume. So what is this area? What is this area equal to? Well, it's equal to the definite integral from A to B of f of x dx, right? It's just an integral, it's just a definite integral. And, okay. Okay. How about this? And there's two methods here. Let's pretend we had a circle. So this is the circle I just cut out right here, the circle. Right? Do you see the circle? Right here, the circle. It's inside, it's a cross section of this base. So it's a cross section. So the circle is the cross section of the space. We call this a disk. So what is the area of this disk? So what is the area right here? Well, what's the area of a circle, right? The circle is what we're trying to do, right? Because when you revolve a function around axis, you're going to create perfect circle cross sections. So, what is the area of my circle? Well, what's the radius? What is this radius length right here? This R right here. What is that length? Well, that length is just the function height, right? See, if I change... Let's see if I can do this real quick. See, if I change my radius... If I change my... It's still the function height, but it's the circular cross-section. So circular cross-section is just... The area of the circle is what? The R is the function height, right? It's pi r squared. Now, I know that's an area of a circle, but the function itself is f of x. And we're squaring that function. So it's pi times f of x squared. Okay, so so we know the area of the disk, right? Wait. We're adding up lots of areas of disks. Alright? So, what is the volume? Well, one disk, we're adding infinitely many disks. Just sort of speaking. We're adding lots of disks. We're adding infinitely many disks for every point in space, right? So the volume so this disk has a width, height, right? This disk has a little thickness. So let's say it's this thick. So it's a little disk. I'm going to shade the disk here. So the volume of this little disk I don't know if I shaded it even great, but this disk right there, the volume of that disk is pi r squared times this little length. And let's call it delta x. So this length is delta x, if you can see it. So that the height of the disk is delta x, the area of the circle. So, guys, remember this is a cylinder. This is basically a cylinder. Right? And the cylinder, is what? Pi of this area? The volume of the cylinder is this area times the height. Right? This is what my cross section looks like. The disk in this case has that volume. Okay, so that's the area of the circle. What's the volume of the disk? Well, it's the area of the circle squared. Okay? Okay. Well, what's the the volume? Oh, what times delta x, right? We gotta do that one, huh? Okay, so what we're doing here is this is the volume of a disk of just the of just any disk. But what we're doing is we're finding the volume of the solid. And the volume of the solid, we can approximate that by adding all the volumes of the disks, right? But they're not going to be perfect, right? Because there's going to be a difference in thickness. And you'll see a picture. I don't know how to explain it. Visually, it doesn't look cool. But you're going to have just a disc here and just a thicker disc. You're not going to have a perfect smooth surface. You're going to have a rigid. So, to approximate the volume, well, I'm going to add up. I want to add up the volumes of these disks. All the way to the last one, which is N. And if you can see where I'm going through this, you can see that this is an approximation, right? We can write this, right? What does this look like? This looks like a summation, right? I'm adding lots of numbers with a pattern, right? So this volume of a solid is approximately equal to the summation from k equals 1 to n of pi times f of x sub k squared times delta x. Okay? Oh, but we want infinitely many disks so that our delta x goes really, really to 0. So, when I'm doing here, and the official term, and I know we're taking n to infinity, if you're wondering, because the exact volume of the solid of revolution is equal to the limit as what? As n approaches infinity of the summation from k equals 1 to n of pi times my function sub k, f of x sub k squared times delta x. Now some people say the norm of the partition approaches 0. And a lot of textbooks have this norm of the partition. And what this means, we'll leave this as n approaches infinity. But what this means, it means n approaches infinity. So with the norm of the partition, this symbol means, this norm of the partition says, hey, my biggest rectangle is approaching 0. Because it's the biggest rectangle, all the other ones have to be smaller. So therefore, all the rectangles get smushed down. So that means there's infinitely many rectangles to fit in that space. That's all that's saying. It's kind of saying the same thing. But it's saying it more in a general term because it's saying we can have different widths and stuff. But this is our volume. Wait, can we make a substitution? Can we make a substitution? And I'm going to erase this integral sign right here. But if we make a substitution, and this is the first time me doing this, but it's just to visually see what this means, because I'm going to turn things into other things. So if I let a u equal pi times f of x sub k squared equals some g of x sub k. Is that okay? So if I let u, and when I say u I'm just going to say u, right? Can g of x sub k equal this right here? Sorry. I'm going to make a little substitution. Can g of x sub k equal this? It's perfectly fine as long as we have these k's here. So we say g of x sub k is a function of that. It's legal to substitute, right? So if we substitute g of x for that, well, let's see what this turns into. Sorry. That is not supposed to be like that. So let's see what this turns into when we substitute that. So the volume of the solid of revolution becomes, what does it become? It becomes becomes the limit as the norm of the partition approaches 0, the summation from k equals 1 to n, or we substitute all this for g of x sub k times delta x. Now, of course, we don't have to write this norm of the partition. We can say as n approaches infinity, if all the rectangles are equal width. So we can do that. I want you to do that. So, hold up. So what is this? What does this look like? Oh, it's the definition of the definite integral, right? It is the integral from a to b of g of x dx. Ooh. What is g of x? Well, g of x is pi times this squared, right? So this equals the integral, this volume of a solid equals the integral from a to b of pi times f of x squared dx. That right there is the volume of a solid of revolution. So that's an important idea. So that's our application. It's a very cool application. Very cool. Hopefully got all of that down. Nice. So, okay. I got this down. Can we do some examples? I want to do some examples. So, let's say I had the function f of x equals the square root of x. Take that. And I want to revolve about the x axis. And this is from 0 to 3. It says find the volume of the solid. So, find the volume of the solid that is formed from this function revolved about the x-axis from that interval. Okay, what does this look like? So, square root of x looks like that. And I have that. And it looks like this solid right here. That's what it looks like. So this is the square root of x from 0 to 3. That's what it would look like. From 0 to 3. So remember the volume. The volume equals the definite integral from a to b of pi times your f of x squared dx. Okay? Sorry, I should probably turn that light on. Okay, let's do that. So the volume is the integral from 0 to 3 of pi times the square root of x squared dx. Here's a very issue. Here's an issue. Here's a big issue, and that is this definition. Remember that definition? So that is the absolute value of x, not... So this is the absolute value of x dx. I want to be very clear that we want to find the volume, right? I want to change this definition real quick. This volume should be 0, right? Right? Is it going to be 0? Maybe. Because remember how we had bottom volume, top volume cancel out? Or the bottom area canceling it. Well, let's see what happens here. Well, is x going to be ever negative? No. No. So we don't have to put absolute values. Because x values are not going to be negative. Okay. What is this? Well, this is pi over 2x squared from 0 to 3. If we plug in 3, well, if we plug in 0, it's going to give you nothing. If we plug in 3, we get what? 3 squared is 9. So it's 9 pi over 2. That's my volume. From 0 to 3 of the root function. Very interesting. Doesn't it seem kind of easy? It seems kind of easy. Let me do another example. I'm going to use a different function. I'll do the same. No. Okay, yeah, well. Okay, so. I'll use the same function. Sure. No, I'll use... Hold up, I'm sorry. I want to use x squared just because. Okay, so... Oh... I'm going to put... So if x squared revolves around the x-y axis... Wait, isn't that kind of weird? If x squared revolved about the y-axis, it would look like this. Right? So this is x squared revolved around the y-axis. Right? As x squared revolved about the y-axis. So we're using that. And our definition kind of changes a little bit, but it's the same concept. So the volume this time is going to be the integral from c to d. I love to use c to d when I do integrals from y. Well, if y equals x squared, here's the thing. If y y equals x squared. I want to solve for x. Well, why do I want to solve for x? Because I'm going to put a dy at the end. So if I solve for x, x equals the plus and minus square root of x, right? And if I say this is, square root of y. So if I do that dy, pi times the plus or minus square root of y squared dy. That's going to happen. So the issue here is, well, this is from 0 to what? To 3, right? Well, think about this. Remember the root function? The root function was like that. And we found the volume. Well, the volume should be the same as this one, right? It should, and it is. I'm just showing you a different way that questions can be phrased. So, the volume is the integral from 0 to 3 of pi times square root plus or minus. Ooh, what's the square of something that's plus or minus? It doesn't matter, it's still plus. So, in this case, y cannot be negative. So this is pi y dy. This is going to be pi over 2 y squared from 0 to 3. We know that the volume is going to be 9 pi over 2. Same volume. It's just in a whole different direction. So watch out for problems that say revolve about the y-axis. Now, there's one problem in particular that looks daunting. And I'm going to erase everything. So what if I had this? I have this special one. So I have this volume right here of a solid. But it itself has a solid inside. And I'm going to kind of call this. So it itself has a solid inside of another solid, and I want to find the region that is between the two solids, the volume between